The SIR model is a model of an infectious disease with three different stages. We have people that are first susceptible, and then they become infective, which means they can infect other people, and then lastly they become removed when they get over the disease and they can't get the disease again or die or whatever it is. This model has three state variables: S for the number of susceptibles, I for the number of infectives, and R the number of removed. And in the transition, the rates of transition, it turns out that a susceptible people get infected at a rate proportional to S times I, with a proportionality constant B, which is infection rate, and infectives recover at a rate proportional to I, so it's A times I, with recovery rate A. To write down a discrete dynamical system model for this infectious disease, let's define some notation. Let T equal time in days, and we'll assume that we're measuring the populations once a day, so these are our snapshots. And so our state variables can be written as S sub T equals the number of susceptibles in day T, and I sub T is the number of infectives in day T, and lastly R sub T is the number of removed in day T. Now we need to interpret these rates. Let's look at them this way. Let's view these rates, since we have a discrete dynamical system, as just being changes. So let's let B times S sub T times I sub T, from over here, let's that be the number of individuals that are infected in day T. Similarly, we will let A times I, or A times I sub T, be the number of infectives that get better, or get removed, I guess, in time T, in day T. These quantities are changes in the state variables, so we can use those to write down our dynamical system. The change in the number of susceptibles from day T to day T plus 1 is just the new value, S T plus 1, minus the old value, S sub T. What should this be equal to? Well, the way that S sub T changes is if somehow susceptibles get infected and they're no longer infected. And this happens, well, on day T, it happens, well, this is the number that get infected, B times S sub T times I sub T. But of course this reduces the number of infectives. So we need this change should be negative. The change in susceptibles is negative because fewer people are susceptible, so we have to put a minus sign here. And our model is that the change in the number of susceptibles on day T is just B times S sub T times I sub T with a negative sign. How about the change in the number of infectives? Well, that's going to be I sub T plus 1 minus I sub T, that's the new value minus the old value. Well, when a susceptible gets infected, then the number of infectives increases, so we should put the same quantity here for the change in the number of infectives, B times S sub T times I sub T. But the I can also change because infectives get removed. And this happens, well, in day T, this number of infectives get better, so we should subtract off this quantity because this will reduce the number of infectives. So the change in the number of infectives should be negative I times negative A times I sub T. Lastly, the removed, same idea. We have the change in the number of removed, R T plus 1 minus R sub T. Well, the number of removed will only increase, and it will increase at, again, this rate. Well, the number that increase in one day will be A times I sub T. So that gets added to the right-hand side. to give us our dynamical system, discrete dynamical system for the infectious disease model with two unknown parameters, of course. We have to, in order to specify this system, we have to determine what are A and B.